All right, guys. Yesterday, we finished off class looking at a static condition example, the sign hanging from two cables. So, let's see what we remember from yesterday. Here is a different object hanging from two cables. Okay? In this case, the cables are actually doing exactly the same thing. Whereas in the other one, we had one cable that was horizontal and one that was angled. That's actually harder. Okay? This one should be a little bit easier. So, you've got these two cables attached to different walls. There's 100 degrees between them. And the mass of the object they're holding is 120 kilograms. I want the tension in those cables. They tell me the tension in cable A because it's the same as B. Okay, I just want the tension in the cables. Okay, so see what you remember from yesterday. What's the key thing we have to remember about a static condition question? F net is 0. The object's not moving. If the object's not moving, it's not accelerating. And since net force is mass times acceleration, net force must also be 0. Okay, keep that in mind. That means the vector sum of all of your forces in this question is 0. Okay, and there's a little vectors in this question. Okay, all right, I'm going to give you a few minutes to try that one. Okay, what force is pulling down on this? Which force? Gravity. Gravity. Okay, can I calculate the gravity? Right. M times G, so that should be, what, 11,772? Is that right? I have a calculator now. I don't have to guess anymore. It works now. I can do that. Okay. 120 times 9.81. Oh, now is one off. 1,177.2. Okay. All right, so we got that in newtons acting down. Each one of these cables pulls at an angle. It pulls up and over, both of them. Whoa. Agreed? Okay. How big is this side for one of the cables? How much does each cable pull vertically?
The same as gravity?
Both of them? Just one of them would pull with half of this force. That's the mistake people make on this one, is they draw this and they write that this is 1177.2. But if that's the case, there's a net force of 1177.2 newtons up if both cables pull that hard up. Okay? They have to split that force. Does everyone follow me there? That's the trick with this question, is I have to split that force between the two cables so that I end up with a net force of 0. Okay? Now, when I split this, this angle is now how much? 50. Okay, that's the other thing I got to split. So I got to split the force of gravity, and I've got to split the angle. All right, so my gravity is going to be 588.6 newtons up. Okay, I've got a 50-degree angle. Can I calculate the tension in cable A now? Right, I've got a side and an angle. I should be able to calculate the tension in cable A. Right, so I have the adjacent side and the angle. I'm looking for the hypotenuse. Okay, so the cos of 50 should equal the side I have, the adjacent side, divided by the hypotenuse, which is what I'm looking for. Okay, so if I want to do this, the tension in cable A is going to be 588.6 divided by the cos of 50. Okay, we have 3 significant digits in that question, so 916 newtons. Okay, do I need a vector? What did we say about tension yesterday? tension is how tight the cable is. Okay? If it gave me a reference, if it said, how hard is cable A pulling on the mast, then I would have to say 916 newtons, 50 degrees left of vertical. Okay, or something like that. Right? But in this case, it asks for the tension in A. That's how tight A is, 916 newtons. Okay? It's also how tight B is, 916 newtons. All right, everybody follow there? Is it the same concept as yesterday? Okay, but one little change, right? Instead of having one horizontal and one angled, now they were both the same, right? And I have to remember that my net force is 0, so I gotta divide that bottom force by 2 because they're splitting it between them. It's these tiny little details that get people on a test or an assignment, right? They're like, they have the whole idea right, and they forget some small detail like, oh, I gotta divide that by 2 because there's 2 cables. Okay? All right. Any questions on that one? Okay. So, if I make this a ramp, does the sled go down right away? Right. When I get to there, it starts to go. Would you agree? Okay. What pulls it down? Everyone wants to say gravity, which isn't entirely untrue. It's just not totally true. Which way does gravity act? Down. Straight down. Which way does this go? At an angle, right? Slightly downwards, for sure. And gravity is the reason it moves in that direction. But is gravity the only force when this thing is going down the ramp? What are some other forces that might be involved here?
Friction.
Yeah, friction would be involved. That's why it didn't start moving right away. Okay, and what else?
The ramp is like pushing back.
Exactly. There's that Newton's third law reactive force that we call the normal force that is present anytime two surfaces are pressed together. Okay? Gravity is pulling the block straight down. That pulls it into the ramp. The ramp has to respond. But the ramp can only push perpendicular to itself. Okay? When it's flat, normal force and gravity are equal. But as soon as I start tilting this ramp, now normal force points out at an angle and gravity continues to pull straight down. Now they don't balance each other out and there's suddenly a net force. And that's what causes the block to slide down the ramp. Okay? That normal force is also what makes ramps so great. Okay? The inclined plane is the simplest machine because it makes work easier. Right? If I'm building a pyramid in Egypt and I've got a big ramp that I gotta take a block up, okay? Well, let's say I just had to get a block to the top of the pyramid, right? Am I gonna lift that thing there? Some of those things weigh as much as a house, right? Like they're not lifting one of those blocks by brute force and carrying it to the top, okay? Or even just straight lifting it to the top, because they didn't have help from aliens, okay? It's pseudoscience, okay? So if I make a ramp, can I push the block up the ramp to get it there instead? Why is that easier? It isn't less work, it's exactly the same amount of work. But why is it easier? What does the ramp do for me? Think about that other force.
It's pushing up against gravity, so that's the only thing fighting gravity.
Right. It fights gravity for me. It supports a lot of the weight of the object. Okay? Like, it's easy to push this thing along on a flat surface, right? Like walking on a level road is really, really easy, but as soon as you get to a hill, it's suddenly harder. Okay? But it'd be way harder to try and jump to the top of the hill because you'd have no help. It would just be your raw strength, okay, that would get you there. But if you have a ramp, the ramp supports much of the weight, and I mean weight when I say that, not mass. It supports a lot of the weight, the force of gravity of the object, which means I only have to get it moving. I only have to push it slightly, as opposed to lifting it to here instead. Pushing it up the ramp is easier because the ramp supports the weight of the box, or much of it. right? That's why the steeper it gets, the harder it gets. Okay, pushing something up a ramp that's like this, okay, is really, really easy. It's barely different from being horizontal. Okay, pushing it up this ramp is quite a bit different, because the more I angle the ramp, the more normal force points outwards instead of upwards. The more normal force pushes upwards, the easier life is for me. Okay, so there's kind of a tipping point for the effectiveness of a ramp. Once you get past 30 degrees, I mean, it's still helping a little, but it's starting to get really steep. Okay, like if you've ever been on like a really steep highway, most of those highways are still less than 10 degrees. Okay, in terms of their incline. Right? It's really difficult to go up anything steeper than that, right? With a vehicle, without worrying about it starting to tip backwards. Okay, everyone kind of follow me there? Okay. All right, so let's look at how an inclined plane works. Okay, I'd like you to write this one down, okay, and draw the picture. We're going to calculate the acceleration of this box. We're going to assume this ramp is frictionless for now, just because that's easier for starting. Okay, so in any question, the first thing I'm supposed to do is draw a free body diagram. Okay, so I want to draw all the forces that are acting on the box. Okay, the most obvious force is gravity. Okay, and gravity acts straight down. Okay, and I can calculate that mass times gravity, right? So m times g. So this will be 98.1 newtons. Okay, it's acting straight down. Right. What's another force acting on that box? The ramp. The normal force, the reactive force. So we call it Fn for normal force. Okay? The normal force of the ramp. Which way is that pushing? Yeah, perpendicular to the ramp. Okay? So it goes perpendicular to the ramp like this. Okay. Are there any other forces? We said the ramp was frictionless, so are there any other forces? Okay. There's two ways to get net force. Mass times acceleration, or the vector sum of all forces. I have no information about initial velocity, final velocity, length of the ramp, time, or anything. I can't calculate acceleration. I don't have it. So what's my only hope? The vector sum. Do I have two vectors there? How do I add vector quantities? I draw them tail to head. Okay? So if I take this force down here and draw it so that it's tail to head, and I did a decent job of making it the right length, I'm going to make one small adjustment here. Just because I had to guesstimate and it came out a little bit long. Okay? So now I've got them tail to head. Where does my resultant go? Okay. Does my resultant always go from start to finish? What do you notice about the green line and the ramp? Yeah, they're parallel. Is that why the box goes down the ramp? The box goes down the ramp because that is what the vector sum of all forces says it must do. Okay? The net force between normal force and gravity is this force, which has to be parallel to the ramp, because that's the way the object will go. It will accelerate down the ramp. The steeper the ramp, the greater that acceleration will be. Because the steeper I make this ramp, the smaller normal force we'll get. Would you agree? Right? The more I make this steep, the smaller and smaller normal force we'll get, because eventually, if I just keep making the ramp steeper and steeper and steeper, eventually I get to this. Does the ramp push on the sled if I put it on here now? What does the object just do? Falls. This ramp is no longer a ramp, it is now a cliff. Okay? And the acceleration will be 9.81 meters per second squared. There'll be no normal force, the object will just fall. It doesn't need the ramp at this point. Okay? But the steeper the ramp gets, the smaller normal force becomes, okay, as you go, right? Until eventually it's gone completely. Does that make sense? All right. So this vector sum here is called F parallel. So you draw two little parallel lines, F parallel. All right, now you're probably looking at that triangle and going, I only know one side of that triangle, Coder. How am I supposed to get F parallel? I don't know what Fn is. I need a side and an angle, or I need two sides. Wait a minute, I need a side and an angle. If this side and this side are parallel, this angle and this angle are equal. They're similar triangles. Okay? It is this angle that results in the object going this way. Therefore, this angle right here is the same as the incline. Now can I figure out what F parallel is? I have the hypotenuse and I've got an angle. It's a side and an angle. I should be able to figure out the other sides now, yes? Okay, so I'm looking for the opposite side, and I have the hypotenuse and this angle. Okay, so the opposite side, F parallel, okay, should equal the sine of 30 times 98.1. Okay, so that is 49.05. Straight down the ramp. Now, if this ramp weren't frictionless, where would I draw friction? Back up the ramp. Friction always opposes, right? Okay. If I was doing the vector diagram, okay, so if I drew this and then I had friction as well, I could technically do this with friction. Now my resultant isn't as big. Agreed? We almost never do it that way. Okay, we just figure out what F parallel is, and if there's friction, we draw it the other way, and then we use two collinear forces. Okay, we use normal force and gravity to get the parallel force, and then we just treat it like they're collinear forces from there on. Okay? All right. Do you need to memorize that triangle? Most people end up memorizing it because we use it all the time. Every inclined plane, the triangle is the same. I mean, not the numbers, but like the forces in it. Okay? Gravity is always the hypotenuse. F parallel is always the opposite side. Normal force is always the adjacent side. And in probably 2/3 of the questions you'll do, you won't even have normal force because you don't even need it. Okay? Unless they bring in something we haven't talked about yet, which is coefficient of friction, you won't even need that side of the triangle for most of the questions we do. So you usually end up just having gravity and F parallel. Okay? So this triangle is always the same. Normal force adjacent, F parallel opposite, gravity hypotenuse. every inclined plane, same triangle. Angle inside that triangle is the incline of the ramp, always. Okay? All right, so we were saying this wasn't gonna have friction, so this is now my what force? It's the net force, right? It's the vector sum of these two forces. Just so happens it's F parallel, but it's also the net force. Can I calculate the acceleration now? Okay, so 49.05 over 10 kilograms, okay? Down ramp. I almost forgot to put a vector in my answer. So at a 30-degree angle, which is only 1/3 of the way to vertical, I'm already getting half of the acceleration due to gravity. Okay? So if you have a 30-degree angle, you're going to be working against your own mass plus a half, okay, in terms of how hard it would be to go up a 30-degree hill. 1.5 times harder than if it was level. Okay, which is way better than like all of it, just lifting it straight up. Okay, but it's gonna be tough. Agreed? Okay. 30-degree angle doesn't seem like much on paper, but if you came up to a 30-degree hill, you'd be like, oh crap, can I go around it? Okay, because it's steep. Okay. All right. Questions on how that one works? Okay, so the only thing that can go weird with an inclined plane is if friction is involved or there's an applied force. So this is, I set something on a ramp and it's frictionless. Well, if I set something on a frictionless ramp, down the ramp it goes. Okay, but some of your questions could be, you have a box at the bottom of the ramp and it's being pushed up the ramp. Okay, is F parallel still there? Yeah, it's the force you're working against to go up the ramp. Okay, it's gonna act down the ramp, but it's sure a heck of a lot easier than working completely 100% against gravity. Okay, going against that parallel force is way easier. That's the benefit of the ramp. Okay, but I've got F parallel acting down and what acting up? Friction's also acting down. Friction's there, but friction always opposes, right? So when I'm pushing something up a ramp, I got gravity acting down, I got friction acting down, and the force up is me, the applied force, me pushing the cart, or if there's a rope pulling it up the ramp. Okay, so you can end up getting a lot of forces that are parallel to the ramp. F parallel always, and friction if it's present, and any applied force, it's either pushing it up or down. The thing you need to remember about friction, always opposes. Okay, if something's going down the ramp, friction's acting up the ramp. If something's going up the ramp, friction's acting down the ramp. Friction always works against you. It's why it's such a drag. Okay. Level frictionless floor. Oh, okay, this is another vector one. You know what, before we do that vector one, I want you guys to do an inclined plane one. Okay. I would like you guys to try number 23. But here's the trick with 23. In number 23, it says it's a 445 Newton box. What did they give you? Like the thing we always confuse with mass. Weight. Okay? If they ever tell you the box is this many newtons, they're telling you its weight. What force is weight? Gravity. This question gave you Fg. Okay? The question never says the object is this many newtons. It's telling you the weight, the force of gravity acting on that object. So it just gave you the hypotenuse of that triangle. Are you probably going to need the mass? You might. If it asks for acceleration, you'll have to get the mass. But that's just divide by 9.81. Right? This question actually doesn't even ask for that. It just asks you to find F parallel. Okay, so draw that one out on paper. Okay, and see if you can calculate what F parallel would be. Right? Hopefully you copied down the last example so you have that triangle in there to help you. Okay, so on this one here, we've got our ramp, here, inclined plane. They tell us that it's angled at 25 degrees and that we have a 445 Newton box. Okay, so we know that's 445 newtons. We know that this force over here is normal force. We don't have it, we don't need it. And we know that this side here would be the vector sum of those two forces, and it's F parallel. It's the component of gravity acting down the plane. Okay, and it's the result of normal force and gravity interacting with each other. All right, can I calculate that side if I know the hypotenuse and the angle? I can. Okay, so what we would have here would be that F parallel is going to be the sine of that angle, because it's the opposite side, times the hypotenuse, 445 newtons. Right? And that's all there is to that question, is sine of 25 times 445. Okay, so 188 points, well, we only have 3 significant digits there, so 188 newtons down the ramp. Now, what if instead of that, I asked for the acceleration of the object? How many more steps would there be? 2. Yeah, there's 2 more steps. If I ask for the acceleration, I've got to do F equals m times a. But before I can do that, I need mass. So then I've got to go Fg equals m times g, and I've got to calculate m. I know what Fg is. It was 445. Divide that to get mass, and then I can plug mass into this formula to get the acceleration after that. Okay? All right. Everybody okay with that one? All right. And then, 13. Yeah, we got time. Okay. This is a vector type of question. Okay? Not an inclined plane. It says it's a level floor. Right? But it's being pulled by 2 different ropes. Okay? So the first one is 35 degrees north of east, and it has a magnitude of 150 newtons. The other one is 10 degrees south of east at 115 newtons. Calculate the acceleration of the box. All right? So free body diagram, vector diagram, sum of all forces. All right, let's see if we can get that one done before the bell goes here. So we need 2 diagrams for this one. A free body diagram, okay, that's going to have our 50 kilogram box, okay, being pulled this way, 35 degrees north of east by 150 newtons. Okay, and our other force here that is 10 degrees south of east but isn't nearly as long, okay, at 115 newtons. Okay, so looking like that. Then, once I've identified that, they say it's frictionless. There aren't any other forces then. Okay, I mean gravity and normal force, but they're level. Okay, it says on a level frictionless floor, so I know they cancel. So now then, I've got to get a vector diagram. Right, so this will be 150 newtons. It'll have an X and a Y, and then I'll have this 10 degrees. 10 degrees, yeah. Okay, 10 degrees at 115 newtons. That means that my net force is this line here. Okay, do we know how to do vector addition questions? That's all that question is. Find the x's, find the y's, add them together. Okay, well, the x's you would add together because they're both east. The y's you would have to subtract because one is south, right? Get your resultant, and then your resultant is your net force. Okay, and then from there, net force over mass, and you've got your acceleration. Okay, is it possible you're going to get ones like that? Sure it is. Okay, you still have to be able to do vector addition. Newton's second law is the vector sum of all forces. All right? So next week, guys, can you just sit down and listen, please? Next week, okay, we're gonna start doing quite a few problems, more you guys working on them and me dealing with the ones that are troublesome, as opposed to me continuing to teach you new examples. I want you to kind of stumble across new examples and see if you can get them figured out using the stuff we've gone over already. Obviously, I'll still be here to help, okay? But that's what we'll be headed towards, and we'll probably do our lab on Newton's second law with the pulley and the cart and everything next week as well. All right, so that's the plan going forward here. Next week is going to be all Newton's second law. Okay? All right.